Plans voiceover. Have you ever wondered why a modern passenger jet can cross an entire continent in just a few hours, yet it almost never flies faster than about 950 kilometers per hour? With all the technology we have today, why are airplanes still stuck at the same speed they reached decades ago? The answer isn't a lack of better engines. It's because beyond this speed, the sky itself begins fighting back. Every day, thousands of passenger aircraft safely cruise through the skies carrying millions of people. Whether you're flying from New York to Los Angeles, London to Dubai, or Chicago to Seattle, chances are your airplane will settle into a cruising speed between 850 and 950 kilometers per hour. It doesn't matter whether it's a brand new jet or one that's been flying for years. The speed remains surprisingly similar. At first glance, this seems strange. Cars have become faster. Computers have become millions of times more powerful. Spacecraft have reached distant planets, yet commercial airplanes appear frozen in time. The reason is that aviation isn't limited by technology alone. It's limited by physics. As an aircraft climbs to its normal cruising altitude of around 11,000 meters, the air becomes much thinner. Thin air creates less drag, allowing airplanes to travel more efficiently while burning less fuel. That's one reason airliners spend most of their journey at this altitude. But the thinner air creates another challenge. Sound travels more slowly at high altitude because the air is colder. Near sea level, sound moves at roughly 1,235 kilometers per hour. At cruising altitude, that speed drops to around 1,060 kilometers per hour. Suddenly, an airplane flying 950 kilometers per hour isn't as far from the speed of sound as many people imagine. As the aircraft accelerates closer to that invisible boundary, something remarkable begins happening around the wings. The airplane itself may still be flying below the speed of sound, but the air flowing over certain parts of the wing speeds up dramatically because of the wing's curved shape. Some pockets of airflow can actually become supersonic before the airplane does. That creates tiny shockwaves. These shockwaves disturb the smooth flow of air that keeps the airplane stable. Instead of producing steady lift, the wing experiences rapidly changing pressure. Drag increases sharply. The controls become less responsive. Fuel consumption rises dramatically. Engineers call this the transonic region. It's one of the most difficult environments for any aircraft to fly through. The closer an airplane gets to this region, the harder every additional kilometer per hour becomes. Imagine riding a bicycle into an increasingly powerful headwind. At first, pushing harder makes you go faster, but eventually, almost all your effort goes into fighting the wind itself rather than increasing your speed. That's exactly what happens to an airliner. Adding more engine power doesn't produce the dramatic speed increase people expect. Instead, much of that extra energy is simply wasted overcoming rapidly increasing aerodynamic resistance. This is why modern passenger jets are carefully designed to cruise just below this dangerous region. It's the point where they can travel quickly while remaining stable, efficient, and safe. But aerodynamic forces aren't the only problem. The airplane's structure is also under enormous stress. Every time an aircraft flies, the cabin is pressurized because people cannot survive comfortably in the thin air outside. While passengers relax inside, the fuselage is constantly pushing outward against the surrounding atmosphere. Think of the aircraft as a giant metal balloon. Each flight slightly stretches the metal. After landing, the pressure disappears, allowing the structure to relax again. This cycle repeats thousands of times throughout an airplane's life. Most of the time, that's perfectly safe, but increase the speed, increase the aerodynamic forces, and those stresses grow significantly larger. The aircraft begins flexing more. Tiny microscopic cracks can slowly develop inside the metal. At first, they're invisible. Then, they become larger. Eventually, if not detected, they can threaten the integrity of the entire aircraft. This wasn't simply a theory. The aviation industry learned this lesson through tragedy. In the early days of jet travel, engineers believed they understood the limits of aircraft structures. Then a series of catastrophic accidents involving the world's first commercial jet airliner shocked the aviation community. Investigators eventually discovered that repeated pressurization cycles had caused metal fatigue around the aircraft's windows. Tiny cracks had spread through the fuselage until the structure suddenly failed during flight. The accidents completely changed aircraft engineering. Manufacturers redesigned windows with rounded corners instead of square ones because sharp corners concentrated stress. They introduced far stricter inspection schedules. They developed new methods for monitoring fatigue before cracks could become dangerous. Most importantly, engineers realized that speed, pressure, and structural durability could never be treated separately. Every increase in speed placed greater demands on the airframe. Every new design had to balance performance with decades of safe operation. This philosophy still guides aircraft manufacturers today. Modern airplanes undergo exhaustive testing before they ever carry passengers. Entire wings are bent upward until they flex far beyond what they'll experience during normal flights. Sections of fuselage are repeatedly pressurized thousands of times to simulate decades of service. Engineers intentionally push aircraft close to their structural limits, not because airplanes will ever fly there in everyday operations, but to ensure they remain safe far below those limits. The result is an extraordinary level of safety. Yet even with advanced materials, powerful computers, and incredibly efficient engines, commercial airliners continue cruising at almost exactly the same speed, because nature has drawn a line in the sky. And staying just below that line remains the safest, smartest, and most economical place to fly. But structural stress and shock waves are only the beginning. There's another invisible danger waiting at high altitude, a narrow zone that pilots fear so much it has earned one of aviation's most chilling names. The Coffin Corner, and understanding it reveals why flying even a little faster can suddenly become far more dangerous than anyone would expect. The name alone sounds unsettling. Coffin Corner. It isn't the name of an accident or a place on a map. It's an invisible region high above the Earth, where the margin between safe flight and disaster becomes incredibly small. At cruising altitude, pilots operate within a carefully controlled speed range. Fly too slowly, and the wings can no longer generate enough lift to keep the airplane in the air. Fly too fast, and the aircraft approaches the dangerous transonic region, where shock waves begin forming and aerodynamic forces increase dramatically. As the airplane climbs higher, those two limits move closer together. The safe operating window becomes smaller and smaller. Eventually, only a relatively narrow band of airspeed remains. This is Coffin Corner. Inside this zone, even a small mistake can have serious consequences. If the aircraft slows slightly, it risks an aerodynamic stall. If it accelerates only a little more, it can encounter compressibility effects that reduce control and place enormous stress on the airframe. Modern aircraft computers constantly monitor speed, altitude, and engine performance to help pilots remain safely within this narrow envelope. But understanding why this happens requires looking at how wings actually produce lift. Many people imagine air flowing smoothly over the surface of an airplane wing. In reality, the airflow is incredibly complex. As air passes over the curved upper surface, it accelerates. The faster moving air creates lower pressure, while the pressure beneath the wing remains higher. This pressure difference generates lift, allowing an aircraft weighing hundreds of tons to remain airborne. At normal cruising speeds, this process works remarkably well. However, as speed increases, Portions of the airflow over the wing begin reaching the speed of sound before the aircraft itself does. Tiny shockwaves suddenly appear. These shockwaves disrupt the smooth airflow that produces lift. Instead of remaining attached to the wing, the airflow begins separating from the surface. Lift decreases. Drag increases sharply. The airplane requires even more engine thrust simply to maintain the same speed. Pilots may notice vibrations known as buffet, caused by unstable airflow striking the aircraft. The controls can begin feeling different. Even though the airplane remains below the speed of sound, the aerodynamics are already changing dramatically. Engineers refer to the speed where these effects first become significant as the critical Mach number. Every commercial aircraft is designed to stay comfortably below this point during routine operations. Crossing it doesn't automatically mean disaster, but it quickly reduces the safety margin that engineers have carefully built into the aircraft. The faster the airplane flies, the more fuel it consumes fighting this rapidly increasing drag. And that's where another major obstacle appears. Economics. Passengers naturally assume that faster airplanes simply require larger engines. Unfortunately, aviation doesn't work that way. Increasing cruise speed by even a modest amount demands far more energy than most people realize. The relationship isn't linear. Every additional increase in speed requires disproportionately greater power. That means significantly higher fuel consumption. For airlines, fuel is already one of the largest operating expenses. Even small increases in fuel burn can cost millions of dollars each year across an entire fleet. Several decades ago, aircraft manufacturers explored the possibility of building faster subsonic passenger airplanes. One of the most ambitious concepts was known as the sonic cruiser. Unlike traditional airliners, it featured a highly unconventional shape designed to cruise noticeably faster than existing aircraft without actually breaking the sound barrier. The goal was simple: reduce travel time while avoiding the enormous challenges of supersonic flight. On paper, it looked promising. Passengers could arrive earlier. Airlines could advertise shorter flight times. The aircraft represented a bold vision for the future. But as engineers analyzed the numbers, an unavoidable problem emerged. Achieving only a modest increase in cruising speed required dramatically more fuel. The operating costs rose far faster than the time savings. For airlines competing in an industry where profit margins are often extremely thin, those additional costs simply couldn't be justified. Passengers generally preferred lower ticket prices over arriving a short time earlier. Eventually, the project was abandoned. The conclusion was clear. Flying slightly faster wasn't worth paying dramatically more. This economic reality explains why today's airliners continue flying at nearly the same cruise speed. Manufacturers have focused instead on improving fuel efficiency, reducing emissions, increasing reliability, and lowering operating costs. Every new generation of aircraft travels roughly the same speed as its predecessor, but it does so while burning significantly less fuel. For airlines, that's a far greater achievement than adding another 50 or 100 kilometers per hour. Still, one aircraft famously ignored these limitations: the Concorde. For decades, it represented the dream of supersonic passenger travel. Crossing the Atlantic in less than 3.5 hours seemed almost unbelievable. Passengers could leave New York in the morning and arrive in London before what felt like lunchtime. It remains one of the most remarkable engineering achievements in aviation history. But extraordinary speed came with extraordinary challenges. At more than twice the speed of sound, the friction between the aircraft and the surrounding air generated tremendous heat. The aluminum structure didn't remain the same size throughout the flight. It actually expanded. By the time Concorde reached cruising speed, its fuselage had become approximately 30 centimeters longer than it had been before takeoff. Engineers expected this expansion and designed the aircraft to accommodate it safely. Even the cockpit contained a visible gap that gradually changed size during flight as the structure heated up. The aircraft also required specialized materials capable of withstanding repeated thermal expansion and contraction over thousands of flights. These engineering solutions were remarkable. But they were also extremely expensive. Operating costs remained far higher than those of conventional passenger jets. Fuel consumption was enormous. Maintenance requirements were demanding. Only a relatively small number of passengers could afford the ticket prices necessary to support such operations. Concorde proved that supersonic passenger travel was technically possible. It also demonstrated why making it commercially successful was an entirely different challenge. And there was one final obstacle that affected not only Concorde, but every future supersonic airliner. An obstacle created not by physics, but by the sound itself. The sonic boom. A sonic boom isn't just a loud noise. It's a powerful shock wave created when an aircraft travels faster than the speed of sound. Unlike the sound from an ordinary airplane, which spreads outward in every direction, a supersonic aircraft continuously compresses the air in front of it. Those pressure waves combine into a single, powerful shock wave that follows the airplane throughout its flight. When that wave reaches the ground, people hear what sounds like an explosion. Windows can rattle, buildings can vibrate, animals can become startled. Even though the aircraft may be cruising more than 11,000 meters overhead, the sonic boom can still be heard across a wide area. During the early years of supersonic flight, these effects became impossible to ignore. Communities beneath test routes repeatedly complained about the constant thunder-like booms. In some cases, minor property damage was reported, including cracked windows and damaged plaster. Whether the damage was widespread or not, public acceptance quickly disappeared. Governments responded by introducing strict regulations. Supersonic flight over most populated land areas was heavily restricted or completely banned. As a result, aircraft like Concorde could only exceed the speed of sound after reaching the open ocean. This dramatically limited the number of profitable routes. A flight from New York to London could spend much of its journey flying supersonically over the Atlantic, but many domestic routes across large countries could not. Even if a supersonic airliner was technically capable of making the trip much faster, regulations prevented it from using its greatest advantage. The business case became even more difficult. Airlines were forced to operate a highly specialized aircraft on only a small number of routes where supersonic travel was legally allowed. That limited flexibility made operating costs even harder to recover. Eventually, Concorde was retired. Its retirement wasn't caused by a lack of engineering brilliance. It was the result of physics, economics, operating costs, maintenance demands, and noise regulations all combining into one unavoidable reality. For modern airlines, the goal has changed completely. Instead of making airplanes dramatically faster, manufacturers now focus on making them smarter. Today's passenger aircraft use advanced flight computers that constantly monitor thousands of systems. Navigation is more precise. Engines burn less fuel. Aircraft are built from lighter and stronger composite materials. Cabins are quieter and more comfortable than ever before. Every improvement saves fuel, reduces emissions, lowers operating costs, or increases safety. Those benefits matter far more than reducing a cross-country flight by a few minutes. For passengers, reliability has become just as important as speed. An airplane that arrives safely, comfortably, and efficiently is ultimately more valuable than one capable of flying only slightly faster while consuming far more fuel. This is why cruise speeds have remained remarkably consistent for decades. Manufacturers aren't failing to build faster airplanes. They're deliberately designing aircraft to operate at the most efficient point possible. At around 950 kilometers per hour, everything comes into balance. Fuel consumption remains manageable. Aerodynamic drag stays under control. Structural loads remain within safe limits. The aircraft avoids dangerous transonic effects. Passengers enjoy a smooth, comfortable ride. Airlines can keep ticket prices affordable. It's a compromise that has proven remarkably successful. But aviation has never stopped searching for better solutions. Researchers around the world are now developing technologies that could eventually change this balance. One promising area involves reshaping aircraft so they generate far weaker shock waves. Instead of producing the traditional explosive sonic boom, future supersonic airplanes may create a much quieter sound that resembles distant thunder. If successful, these designs could satisfy future noise regulations while allowing faster travel over land. Engineers are also experimenting with entirely new aircraft shapes. Long, slender fuselages. Highly swept wings. Advanced, lightweight materials. Powerful computer-controlled flight systems. Every improvement is aimed at overcoming the challenges that prevented earlier supersonic passenger aircraft from becoming commercially successful. Modern engines are becoming more efficient. New manufacturing techniques allow stronger yet lighter structures. Computers can optimize aircraft performance in real time, making adjustments impossible for human pilots alone. Together, these advances may finally reopen the door to routine supersonic travel. But even if that future arrives, the laws of physics won't change. Air flowing over a wing will still create shock waves. Heat will still build as speed increases. Fuel consumption will still rise. Engineers won't eliminate these challenges. They'll simply find better ways to manage them. For now, every commercial airliner flying overhead represents decades of engineering experience and countless lessons learned through research, testing, and history. That familiar cruising speed of around 950 kilometers per hour isn't an accident. It's the result of finding the perfect balance between speed, safety, efficiency, durability, passenger comfort, and operating cost. The next time you look out the window during a flight and wonder why the airplane isn't traveling twice as fast, remember that it isn't being held back by a lack of technology. It's flying at the speed where science says it performs best. Beyond that invisible limit, the air itself becomes a powerful opponent. Shockwaves begin to form, drag rises sharply, structural loads increase, fuel consumption soars, noise regulations become a major obstacle. Every extra kilometer per hour comes at a much higher price. That's why modern passenger airplanes don't fly faster than about 950 kilometers per hour. Not because they can't, but because, for today's world, it's the smartest speed to fly.